Welcome everyone to this tea talk. It gives me great pleasure to introduce Matt Taylor. So Matt is visiting us from University of Alberta, Amii, the other AI institute, and he's going to tell us about human and agent cooperative learning. Matt.
All right. So before handing the mic over to Matt, let me remind you all of some house rules. So as usual, questions will be allowed to be asked during the talk, only clarification ones. For people online, in order to ask your question, you just have to raise your hand and I'll give you the mic to ask your question so that people online can hear you. For people online, you just have to type question or I have a question in the chat. And when the time is right, I'll let you directly ask it. Of course, there'll be some additional time at the end of the talk for people to ask further question or have a more informal discussion with Matt. And after that official Q&A period, Matt will be available for a few minutes before going to lunch to have more offline discussion. That's pretty much it for me. So whenever you're ready, Matt, the floor is yours.
Awesome, thank you. And I am available after today too. I'm not leaving Canada. So also one more affiliation in the list is I do work with AI Redefined. So they are responsible for flying me out this time. So thank you. So I was trying to figure out what I wanted to talk about today. And the first step was getting my slide advance working. There we go. So good. So I think my guess is everyone's on board with reinforcement learning is awesome. Starting from the super important American options exercise policy, but it was one of the earlier examples of RL in the real world. And then we saw AlphaGo. That's great. Video games are awesome. Everyone loves good video games. But what about the real world? Well, now we've seen examples with data center cooling, stock trading, balloon control, fusion. Adam White was here a few weeks ago talking about water treatment. This is great. But when we're thinking about what do we want to accomplish as researchers, there's differences between what we do in the lab versus what we get as a proof of concept versus something that we can actually deploy. And thinking about what's going to be next. So a lot of our group's work has been what's going to be the next thing? How do we make the next thing more accessible? How do we make reinforcement learning more useful in the real world? So I think about this in two kind of ways. The first one is more from a business side. How do we better find good reinforcement learning problems? What's a good business problem that reinforcement learning can solve today? How do we identify problems that will be impactful? How do we get solutions quickly? How do we de-risk it? Not going to talk about that today. Instead, I'm going to be focusing more on the second part, which is I want to cheat. I want to cheat a lot. Now, this is, people are familiar with Rich Sutton and his viewpoint. This is pretty opposed to what he thinks. So Rich is much more about how do we learn everything from the ground up? How do we minimize the amount of human knowledge? And I think this is a good long-term research direction. That's probably the right way to get really powerful algorithms. But I'm going to argue today that if we want to get reinforcement learning working today, or within the next 6 months, then we should figure out how do we put as much bias into our algorithms as we can. Now, of course, this might prevent us from reaching the optimal, we often don't reach the optimal policy anyway. But in practice, how can we put this bias in there? Well, we can think of how do I use existing data, existing agents, or people? So for example, if I am trying to optimize a plant, I have a chemical plant that's been operating for 10 years, I can plop my reinforcement learning in there and it could start making taking actions in the real world. And it will start making mistakes in the real world. Instead, if I've got a bunch of data, why not use that? If I've got a PID controller, a model or MPC, why not use that? If I've got a human operator, Joe, who's been working at the plant for 10 years, why not use his knowledge, his background? So that's what I want to talk about today, is thinking about these different data sources and how we might use it for reinforcement learning. So what we've been looking at for the past, probably 10 years is thinking about cooperative learning. So instead of just a single agent in the environment, let's think about having multiple agents or humans. So we could think about how, for instance, one agent could learn from another. So this will be, my talk has 3 parts. First part is looking at how one agent could help another. And the second part would be how a human could help an agent. And then lastly, I'll end with something that is newer to our group, which is how an agent can help a human. That's kind of the 3 parts of my talk. And it's going to be fairly high level. I'm going to go into a little bit of details on some of the methods. But the main goal, well, I guess there's 2 goals for today. The first goal is to try to convince you that it's worthwhile thinking about other people and agents in the environment when you're doing reinforcement learning. And many of you are already doing that. The second one is for the students in the audience to give you a few citations that you could go and look up and some pointers to where you could quickly learn more. I was just reading a blog post on ChatGPT and RLHF, reinforcement learning from human feedback. And at the very bottom, there was a footnote thanking Peter Stone for pointing to references to older work, like my paper from 2016, super old. So I'm trying to show some of the older work to the audience for kids these days. Okay, let's talk about the first one, thinking about agents teaching agents. Now, most people are going to assume that the prior operation of the plant, prior agents you see were not perfect. But you should be able to use that for bootstrap learning. So one of the ways you can do this is batch RL or offline RL. There's a citation here by Sergey Levine and others. If you're interested, I think this is a good entry point. And here, some of the questions are, if I have a policy, can I use my data to understand how good that policy is? The policy evaluation. There's also, if I've got a bunch of data, can I learn a good policy? Can I improve that policy? And then there's questions about how much data do I need? And then how sure am I that my policy is performing well? So one of the things we and other people have been looking at is, if I've got a bunch of data, how can I learn a good policy? And when do I say I've got enough data that I'm willing to deploy? So going back to my chemical plant example, I've got 10 years of data. Well, it turns out when they're operating this plant, they never tried this action. So if I'd never seen that action before, I can't really say much about it. But you could potentially ask the person to show you that action and maybe generate some more data. And at some point you could say, okay, Bob, you take a rest. We've got it from here. Or at least, hey, Bob, let me try controlling the plant, but be ready to hit the emergency stop. So you could put some bounds and guarantees on that with things like off-policy evaluation and high confidence off-policy evaluation. Another thing you could think of doing is transfer learning. So this has been around for a while. And here we think about not just data, but I've got an existing agent usually. So I've got some agent that's learned how to control a task, how to perform some task. And then I want to take that knowledge and give it to a new agent. So there's questions about, like, what should I transfer? Should I transfer like a high level policy, low level Q values? What happens if the source task is slightly different from the target task? There's questions there. There's also the question of when to transfer. So if I really care about this difficult task, how much time do I spend on the simple source task before I transfer to the difficult one? So there's ongoing questions there. The thing I want to emphasize on this slide is, if you've got an existing agent, don't throw it out. I mean, that seems obvious, but we see so many papers where as researchers, we're really interested in training our agent from scratch. That's great. But if we're thinking about deploying stuff in the real world, chances are there might be an agent you can leverage. And one recent work I'll highlight that we worked on was actually in energy and buildings. So I've been getting a real kick out of trying to bring reinforcement learning again out of video games and into other domains. So here what we were doing is trying to, there we go, learn with diversity. So think about, I've got some source task. I've got a source task or source tasks, and I want to learn how to, in this case, optimize an HVAC. And so think about a maze domain. I can find the optimal policy, the optimal path to the goal, but maybe there's a few other ways that are near optimal. Similarly with building control, maybe I can find a number of good ways of controlling these buildings. So I can build up, instead of a single policy to transfer, I can build up a library. Once I have this library of policies, then I can do something. I mean, I could, if I had infinite time, I could take each policy from my library and evaluate it in the target task. Of course, that's going to be infeasible. So we can do tricks like clustering and picking a representative policy from each of these clusters. We can do things like off-policy evaluation, where we were saying, when we were just saying with batch learning, when I look at each of these policies, I get a little bit of data in the target task and figure out which policy to grab and use. And this can be much faster than learning from scratch. You could also use this for things like sim to real transfer. But here's an example where if I don't have a lot of data on the target task, on the thing I really care about, maybe I can use something I learned on a similar task. If I care about the real world, I probably don't want to learn from scratch in that real world. Curriculum learning, another popular choice. If you're interested in learning more, here's a survey I can recommend. Not at all because I'm one of the co-authors, just happenstance. In curriculum learning, you think about, if I've got this final target task, what's a sequence of tasks I can use to get there and learn that sequence faster. And this could be automatic. It could be through a person. There's different ways of doing this. And I'll also finally mention there's also multiple meta RL methods. So we have this framework called reinforcement teaching, which in reinforcement learning is a way of doing curriculum learning. So in reinforcement teaching, we have a reinforcement learning agent that's teaching a student, and that student could be a reinforcement learning agent itself, or it could be a supervised learner, or something else. But I wanted to just give you this high level overview of different ways that one agent could teach another. So then the last point I'll talk about is thinking about giving advice. So with transfer learning, I normally assume I can grab the source agent and take its brain and stick that into the target task agent. Well, what if you can't do that? What if the source task agent is different? So if it's a rule-based agent or a PID controller, what if you don't have an unlimited number of queries? What can if I can only ask my teacher for help a few times? So thinking about, well, I've got this new agent that's learning something, and how can a more experienced teacher help it? Now, again, the teacher isn't perfect. We can't just treat its word as gospel, but hopefully we can learn from it. There's lots of interesting questions here that many groups have been looking at. So thinking about what information to provide, when to provide it, is there a cost? What if I've got multiple teachers? Who should I listen to? And the kind of things you see in this area is you say, look, I can learn with no advice. And then if I use advice, my learning curve is higher than using no advice. So, okay, this is great. This is a great paper, right? My line is higher than your line, so I can publish. And we could do lots of stuff here showing that, oh, well, we can learn faster and be slightly more efficient. One of the drawbacks of many of these methods, and particularly learning from advice, is there's very few theoretical guarantees. So these often work in practice. If you have a teacher that knows something, not perfect, but knows something, there's lots of ways to leverage that teacher and learn faster and bootstrap and eventually reach near optimal performance, but there aren't a whole lot of guarantees. So I wanted to catch my breath and say, okay, here's one paper where I'm going to go a little bit more in depth. This is work from Sriram, who's a postdoc now with Vector. And in his work on multi-agent advised or Q learning, he's thinking about having multiple teachers that you could listen to. And, oh, excuse me, he's in a multi-agent setting. There's multiple students and they've got a teacher they can listen to. And the reason I wanted to point this out, this Gimler paper from 2022, is that Sriram actually has some theoretical guarantees, which is not that common in this advice framework, because most of the time it's the kind of papers I usually write is exactly what I was saying. Look, my method learns faster than yours. It's quantitatively better, so please give me a publication. But I really like Sriram's work because he was going deeper and saying, well, can we really give some guarantees that this will actually work? So here's the setting. We've got multiple agents that are learning something. So I was saying this is cooperative RL. Well, I'm thinking about here like a team of reinforcement learning agents. And that could be one team playing against another, could be just a team cooperating, but let's just think about the team. So we've got these N agents and they're interacting with an environment and they've got to select this joint action. And what Sriram was looking at is how can we improve sample efficiency? How can we learn faster? So he wants to have very few assumptions on what this advisor is going to do or the environment. And he introduced two practical algorithms for how we can leverage this with theoretical guarantees, which I'll get to. So, okay, I need to, every talk should have one slide with tons of symbols. So here's ours. On the left, we have the normal MDP setting. And on the right, we have the stochastic game, which is the generalization of an MDP to multiple agents. So we can think about having a shared state space. These different agents are all selecting their own actions. There's some reward per agent, and they're trying to maximize the sum of expected discounted rewards. So the first, pro tip, when you come up with an algorithm, come up with a cool acronym. So much better than just saying Taylor et al. Said, no, Admiral, advising multiple intelligent agents. So we're, in this case, the Admiral algorithm, the idea is we've got some external source of knowledge. So I said I've got a teacher. And that could be a Q learning agent, that could be a genetic algorithm, that could be a PID controller. And our teacher, this advisor, can give recommendations to the student. And we're going to learn online. We've got each agent has access to one advisor. And the agent can say, am I going to listen to this advisor or not? So if the advisor was perfect, this is trivial. You just listen to the advisor on every time step. Done. Of course, our advisors aren't perfect. And we're assuming free communication. A few other notes. We've got a fully centralized setting. Everything's observable. And then there's two kind of scenarios we're looking at. The first one is Admiral DM, the decision-making algorithm. This is, I've got my team of agents. Each of them is looking at their advisor and trying to decide, who do I want to listen to? Do I want to listen to myself or do I want to listen to my advisor? And then there's also this second algorithm, which is more just trying to quickly understand how good your advisor is. Because if your advisor is garbage, you're probably not going to want to listen to them very, very much. Okay, so I want to just give a sketch of the algorithm where we're trying, so here's the Admiral DM. We're trying to choose, each agent is trying to choose whether to listen to the advisor or not. And one way to do that is have some decreasing probability. So over time, you want to listen less and less to the advisor. And you can kind of set that in part on how good the advisor is. And you balance that all again with exploration. And this is a greedy in the limit with infinite exploration algorithm. So let me just show what this looks like in practice. So when we start, we've got some initialization. And then we try to figure out, we start with the initial state, let all the agents sample actions. And then we've got this loop where we execute rewards and then choose an action based on either each agent chooses an action either on its own Q values or the advisor. And then over time, it can figure out how to listen more and more to itself. So this is not the brilliance of this paper. No, the algorithm in this paper is not overly complicated. What I really like about the paper is Sriram's theoretical analysis. So what he wanted to do is try to provide some fixed point guarantees. So to say, well, if our team of agents does this, eventually we're going to reach a Nash equilibrium. So we can get to that Nash equilibrium. And with the decision making, we can show that this algorithm will converge to the Nash equilibrium regardless of how good the advisor is. So empirically, we'll show that, oh, we can learn a lot faster. Well, if your advisor is good, that's not too surprising. But even if your advisor is good, you're going to converge to the same place as if even if your advisor was bad. So this is nice to have that kind of guarantee that if the person you're listening to is not very good, you won't get too far off topic. Oh, and the other algorithm was showing that, oh, we can, if I'm evaluating these advisors, I will get within epsilon of the correct value of these of each advisor. So that we looked at this empirically in Pommerman, which is Bomberman, but partially observable. We also looked at the simple games of Pursuit and Waterworld. And actually, I'm going to skip this, some of the details. What we looked at is showing advisors with different abilities. So we're able to show with a good advisor, we are able to quickly learn to evaluate them as good. With a bad advisor, we could quickly learn that they were bad. That's not too surprising, but being able to do it and prove that we could do it. And then also with the decision making, can I quickly use this advisor to learn to outperform a competitor? And we compared to learning from scratch, which isn't too surprising. If I have a good advisor and he doesn't, I better be able to beat him. But we also looked at other methods that existing methods that were able to leverage this advice. So yes, Rupali.
I have a question here for the graphs. So I'm assuming the DQN and the DQ from demonstration, they're the agents which are learning from scratch.
So with DQFD and chat on the bottom, those are both learning with the advisor. It's only the DQN in the upper left that's not using the advisor at all.
And is there any like brief explanation to why their cumulative reward is actually going negative?
Oh, sorry, because this is Pommerman. So whenever our algorithm wins, it means that their algorithm loses. So by the Admiral DM algorithm is learning faster than these other algorithms, which means that its reward is positive and their reward is negative because it's a direct competition.
Oh, it's a competitive setting.
Yes.
Okay, gotcha.
Yeah, that's the whole Bomberman blowing the other team up.
Okay, thanks.
Awesome. Actually, any other clarification questions while we're here before we head into the second part? Yep, there's a question in the back. And I'll just pause.
So you said you can beat up the competitor and learn faster, but you will always reach maybe the level of the advisor, but not better than the advisor, right?
Oh, great point. So if my agent was limited to the advisor's performance, I'd be very sad. Because if part of the motivation for this is if I have a plant that's controlled by a P&E controller, I don't want to just do imitation learning. I want to be able to outperform it. So that's a great point. Thank you for that. Now, in this case, in this particular work, we show that we can converge to a Nash equilibrium where no one can get better. But in general, we're going to be able to learn to outperform the advisor or the teacher. If we can't do that, these methods wouldn't be nearly as interesting.
Thank you.
Okay, then I'm going to plow ahead and say, often when I give talks, I focus just on this part, the human teaching an agent, saying we've got all of this great expertise around us. Why don't we use it? So there's a couple of places where we can think about learning from humans. The first one is what if there's no reward signal? So now I'm not in an RL context, but I'm just in an MDP. I've got a sequential decision process. So I could learn from demonstrations. And we can think of imitation learning or learning from demonstration. This goes back to at least the early 90s with robotics. I believe even before that in simulation. Think of teleoperation or manually moving a robot arm. We just want to get the agent or robot to duplicate what you're doing. Could also learn from human feedback, which I'll get into a little bit. Or we could learn from human preferences. So humans saying that trajectory A is better than trajectory B. So think about when you go to the optometrist's office, number 3, number 4, number 3. So then by picking these preferring one trajectory over another, you can learn pretty well. So we can think about, and when we think about human teaching an agent, now we really need to start thinking about UX and UI. How do we get the human to give us good feedback at the right time in the right way? And then of course, there's also the, what if there is a reward signal? So I could have a demonstration and I could use that to bootstrap my learning. So I try to mimic the demonstration and then I use the reward to outperform the demonstrator. Or I get a human feedback and that can help me bias my exploration to learn faster. Human preferences, action advice. This is similar to what we were just talking about before. So instead of, now we could have a person come and say, agent, you should go up. And if you trusted the person, you could memorize that. You could say, well, whenever I'm in state 52, I want to go up. Or you could just use that one time to kind of bias your exploration. And of course, you could have a person give shaping rewards. So kind of, I think of this as throwing cookies at the dog as it's going on its way towards the water bowl. So let me give one of these cases. Let's say I want to learn from human feedback and there's no reward signal. So we could go back to Andrea Thomas and Cynthia Bazile, where they did an experiment in Sophie's Kitchen, where they just had a human give reward. And they treated that human reward as the environmental reward. And they found something kind of interesting. What they found is that humans would give rewards anticipating what the agent would do in the future. So for instance, if the agent's supposed to go towards the counter, if they thought the agent was going to the counter soon, they could give rewards, which is kind of weird because normally as a reinforcement learning person, you think of, I want to give rewards for what the agent has done, not what I think it's going to do. So there's a bit of mismatch there. And you read that and like, oh, wow, these people are stupid. Yeah, people, man, they're hard. Human subject experiments are hard. We don't really know what people want or what they're doing. Well, okay, so if people aren't really giving rewards, another thing we could think about is, what if people were giving something to do with the return? All right, so remember the return is the sum of the future rewards. So maybe the people are just saying, if something was good, that means you took the action that was going to get you the best return. Well, if that were true, if the people are already kind of doing this look ahead, then this could just be supervised learning. I could say, oh, well, the person is just telling me what's the best action. Awesome. I could just look at what the human is telling me, good and bad. When it's good, that's the optimal action. And when it's bad, I've got to explore again. So we could say, well, this is just a numeric reward and it's the return. There's other work, and I should say Brad and Peter did some awesome empirical work showing that this was extremely efficient learning. Humans are very good at this. But then other people came along and said, well, does it really make sense for this to be numeric? So if I'm saying, in this case, if I say sit and the dog tries to shake and I say bad dog, or if I say sit and the dog sits and I say good boy, is that really a -1 and a +1? Well, it turns out you could also treat this as categorical feedback. And there's some evidence showing that people do give their feedback in terms of categories and you can learn faster in some cases. And then there's another algorithm where McGlashan and others were saying, I want to give feedback. In this case, I've got this dog and I want the dog to get to the yellow goal state and not go over the green grass. So let's say that the dog goes right over the grass. So that's bad. Now, we could also say, what if the dog goes to the left, up and around? Well, that's all right. Didn't go over the grass, but that's a suboptimal policy. Or you could have the dog do the optimal thing. So let's look at these three conditions. And again, going back to human subject experiments, humans are noisy and annoyingly confusing. But let's ask them. Let's have humans say on a scale of shocking the dog with a shock collar up to giving treats. How would you give feedback to this dog? So let's look at 3 conditions. The first one, we're going to show the human a trajectory in the upper left. The dog goes across the grass, show it once, dog goes across the grass, and then show the third trajectory where the dog does an okay thing. So this is improving. The dog got better. Third case is just show that middle one 3 times. Third case is degrading. We show the good, and then the all right. And now we ask for feedback. So if we were giving feedback in the tamer way or the sable way, all 3 of these cases, the human would be expected to provide the same feedback because the human could be just evaluating what the agent just did. But instead, what we see is the humans say, oh, well, I'm not just going to care about what just happened. I'm going to look at this trajectory of performance over time. If the agent's improving, well, then I'm going to give him more feedback, positive. If it's getting worse, then I'm going to give the agent more negative feedback. And it turns out this is the advantage function. So looking at the difference between V and Q in RL parlance, and we can show that that can work. So here's 4 different ways of interpreting human feedback with no reinforcement learning signal. So when we talk about, and I should emphasize that we don't know which one of these is going to be best when. These are all just different hypotheses that in some cases seem to work better than others. We don't necessarily know which is going to be best or why, or how we could bias humans to give us the kind of feedback we want. These are all open questions. The reason I wanted to go through this was to kind of emphasize is when we say reinforcement learning from human feedback, that can mean a lot of different things. Is there a reward signal or not? How is that feedback happening? How are you assuming the human is giving it to the agent? So we as computer scientists probably aren't going to have all the answers. I mean, of course, we always have the answers, but we could use a little bit of help from, psychologists and education people. So this is really, I think, an interesting multidisciplinary question. What's the right way to try to learn from people? How do people want to teach agents? How can we make the best use of that? So if we acknowledge that we have an agent and there's a human in the environment, we probably want to figure out how to leverage that human somehow. Now, again, if the human is completely clueless, or if the human is adversarial, then we've got a whole nother set of problems. But assuming the human is competent and helpful, we should be able to leverage something from them. One other dimension I wanted to mention is what we're going to assume about this person. So we've been doing a bunch of experiments with lay people. So just people on Amazon Turk, undergrads who want a bit of candy as they're walking through the hall. But you could also think of having subject matter experts. So thinking about someone at that plant, or thinking about if you're working at AI Redefined and thinking about controlling drones, having a drone operator who actually knows what they're doing. You could also think of having a programmer. Now, most people can't program, but let's suppose you've got someone who could program. Well, one thing you could think of doing, this is an experiment we ran a few years ago, is getting people who had just completed 2/3 of an AI class to give heuristics to agents. And it turns out they can do this quite quickly. So they can write down, I believe it was a Python function describing similarities in the state. And in just a few minutes, they can write down a function that helps agents learn a whole lot faster. So that's not too surprising. If you can have someone who has that kind of ability, you should be able to use it. But again, most people don't have that ability. So thinking about, what I go back to is my dad can train a dog. My dad can train a dog. He ought to be able to train a robot. Shouldn't we be building robots that can learn from him? All right, so that was kind of the second part where I just of the talk where I was trying to motivate the use of humans. That sounds bad. I was trying to motivate how humans and agents should work together for the betterment of the agent's reward. But But then the last direction I wanted to go was thinking about, what about intelligent tutoring systems? So for those of you who haven't been familiar with aren't familiar with these have been around for decades, and they're often in very procedural settings. So think about teaching a person how to do multiplication, how to do long division. There's a very rigid set of steps that you take. There's an order that you take them. And when you mess up, it can be clear what you're doing wrong. When you're doing this, you want to teach the person something. You want to convey some information. And in order to do that, you probably need to understand what the person does or doesn't know, or at least have an estimate of it. And this could be particular steps in a procedure, or this could be more general, like, oh, they don't have enough spatial awareness for this task. They don't really understand how acids and bases work together. So I need to take a step back and try to teach that general concept. So we want to figure out what the person knows. And ideally, we'd also like to understand this person's capabilities and how they would learn. So think personalization. How does this person want to learn? Do they want to be spoon-fed answers? Do they want to struggle with it? So can we personalize to a particular learner? And what we've been thinking about is, I was saying, well, I want agents to learn from agents. I want the agents to learn from humans. So why not that third direction? Why not look at how humans could learn from agents in sequential decision tasks? So we've been pushing on this a bit for the last few years. We have got a AI in education paper coming up, and this was work by my student, blanking, oh boy, my student Callie and my postdoc Christabel, and they were looking at, the motivation was, oh man, I procrastinate a lot. Can I learn to not procrastinate? So what they did is they have this MDP that they're trying to teach people how to perform it. It's called the Mouse Lab MDP, which is from the existing literature. And they're trying to teach people how to solve this MDP, and we can make the argument for why learning the optimal policy in this MDP is related to learning to not procrastinate. But for now, the main point is that we're looking at how we want a person to practice on their own. How do we provide support, and when do we provide it? So do we want to just show them the correct policy? Do we want to show them the next node, the next state they should have visited? Do we want to do that right away, as soon as they make a mistake? Or do we want to wait until the end of the episode? And right now we've got a few answers, but mostly more questions. But trying to think about how we can teach people these concepts for a simulated MDP. And boy, if we could get this right, then what else could we do? Well, we've also been working with a flight training company. They're called Delphi, and they're out of Manitoba. They also have offices in Calgary. And they're saying, well, it turns out there's a shortage of pilots, not just in Canada, but at least in North America. Many more are retiring. Right now, in order to learn to become a pilot, you need a pilot to teach you. So that seems like kind of a catch-22. And of course, that pilot needs to be a lot more trained than the student is. So one thing you could do is, instead of having, and the normal way to do this is you have the student sitting next to the pilot up in the plane. And instead of doing this, what if we have an intermediate step of learning and simulation? Okay, you could have a student learning in simulation and a pilot sitting next to them. That's much more cost effective. Or what if you have 20 students in simulators and you have 20 intelligent tutoring systems, one for each student, one for each person that's giving them advice. And you can have that intelligent tutoring system be able to raise up its hand and say, pilot, please come rescue me. My person is so confused. I have no idea what he's doing. We need professional help. So in this way, you might be able to scale up training. And if we're thinking about learning and simulation, the pilot training, why not also have flight school be online? So instead of making everyone sit in a class in real time, why not bring some of this into the virtual reality? So For now, I'm just going to talk about the flight training, but we are handling both the information learning, the pilot school, as well as the physically handling the plane. So first, when you're thinking about how do you learn to fly, one of the first tasks is straight and level. This is what it sounds like. The plane is going straight and it's level and you're not messing up. It turns out it's actually not trivial. Who knew flying planes was hard? But so we define the first task, and then we get a human expert, a pilot, to do a bunch of demonstrations. So now we can have our AI teacher is an RL agent. That RL agent can imitate the human expert. Okay, so now we're going back to the agent learning from the human. That's cool. And then, but let's assume our expert isn't 100% perfect. Let's assume they're really good, but not quite perfect. Well, in that case, we can also define a reward function. So a subject matter expert can define a reward function for this task. And now our RL agent can bootstrap off the demonstrations, but tweak its policy to learn an even better policy with this environmental reward. Okay, so now we have our teacher agent. And now we have a bunch of students come in. Now these students start trying to fly the plane straight and level, and we can have our agent give feedback to that student. So I'm afraid my sound isn't working today, but here's what the simulator looks like. We're using X-Plane. It's a high fidelity simulation. Even though it's actually pretty good graphics, we can access it over the internet. So right now we've got a bunch of, oh shoot, I think they're called junior air cadets. So think like high school students who might want to go into the military or learn how to fly. They can do this from home on their computer.
Maintaining a level aircraft.
Oh,
agent observes the
what is the sound?
key flight parameters.
Okay, I'm going to turn him off. So here you can see what it looks like from the cockpit. So you've got a certain place you're flying to, and then just going to skip over the imitation learning bit because I already covered that. And then we can show, okay, our agent is able to learn over time. That's not too surprising. And then what we can do is have our agent look at some students and have both known errors. So ask the student to mess up, make sure we can catch it, but also just have students fly and see if we can catch their errors. So in this case, the student it was taking a while for the student to center there. So I'm going to pause here. So here we can see trajectories of how the human flew, but also what the agent would have done in those different circumstances. So we're thinking about at every time step, can we think about what would the agent have done here? How different is that from what the human did? Or we can look ahead 5 seconds. How different is the place that the agent would be in 5 seconds versus where the human ended up? Ooh, that really was bad. That was an error. So let me come in and correct it somehow. So some of the ways we're correcting it is giving some visual advice. So it's trying to show if your roll and yaw, or excuse me, the pitch and roll, how that's relative to what you should be doing. So that's one way of giving the user these visual hints for how they should be able to fix how they're flying. And another example, oh, and here you can see it. So you've got this little heads up display and trying to teach the user, hey, there you go. Teach the user the way to correct. Yeah, Rupali?
Hi, a quick explanation here. The ground truth or the expected behavior is coming from the agent or from a human expert? Sorry, I think I missed that part.
Good question. Here we go. So we've got the human student flying, and then we've got an agent that's trying to correct.
Okay.
Now, this agent learned both from an expert pilot and from itself, from self-training through reinforcement learning.
Okay.
But at this point, we're just assuming that the teacher agent is near optimal. Then the question is, can it recognize when the human student is messing up? How bad is the mess up? And then how can I give advice to the student to fix it? So in this case, we're giving this advice in real time, saying, whoa, you should go over here. But you could also think of like after action review, sitting down with a student and saying, okay, at time 34, you went this way and you should have gone that way. And actually, let me show you what that looked like in the cockpit. Let me show you what it looked like outside of the plane. So there's lots of cool things we can do. Because it's in simulation, we can roll back and we can go look at things from different angles. We can look at different counterfactuals.
All right, thanks.
Question?
So earlier when you mentioned feedback, you said something about looking ahead. Could you clarify what you meant?
Yeah. So we could think about, we normally think about feedback as just you're doing something wrong. But if I'm in simulation, if I've got a simulator, I could do rollouts and say, well, I see where the human is about to go based on their actions. And my action says you should do this. I know my policy, so I'm going to roll out my policy 5 seconds ahead and see there's a huge divergence.
Divergence in terms of what?
In terms of the state. So assuming the teacher is going to follow a good trajectory, then you could see, oh, well, if these actions are similar but end up in very different states, that's probably not good.
But what if these different states have similar rewards? I mean,
Then you're fine.
but okay, so you're also checking the reward there.
Yes. Yeah. So we can also do that. I mean, we'd look at the value of the state that you end up that 5 seconds ahead.
Okay, thanks.
Awesome. So, oh, another question.
And so with the visual cue, aren't you afraid that the students are just going to learn to follow this cue and not care about the surrounding anymore?
Yes. And that's so the question was, how do you give the right amounts of support? Because if you're doing driver's ed and the person who's trying to teach you is always, oh, you're doing it wrong, let me take over. Like that's never going to work. Or if the person's always yelling at you, slow down, slow down, slow down, then you might come to rely on that. And that's a great question. So it's trying to come up with the right amount of support at the right time. So if we always showed this correction, you're right, it could become a crutch. So we need to think about when to remove it, to test the person without these supports, because that's ultimately how they're going to be tested. So this is ongoing work. There's a lot of open questions, but I wanted to bring this up because I think it does fit in with the other stuff I've been talking about. We're thinking about, I've got a source of knowledge, in this case, an agent. I've got something that's learning, in this case, a teacher. How can we provide that information? You know, in this case, we're providing feedback, but you could also think about the teacher providing demonstrations or the teacher providing advice. All of these, many of these different modalities could still apply. So the last piece I'll mention is something that's coming up at ICHCAI. This was led by Fatima. She finished her master's and is currently looking for opportunities. So if you are interested, I would be happy to connect you with her. But here we're looking at something a little bit different and saying, I want to help a person write code better, faster. Well, okay, use Copilot, done. Well, okay, well, let's say I want people to write code for a reinforcement learning problem. Well, now I've got a reward function that I could try to optimize. So I could have a person write code, and I want my system to improve that code. I want to have it improve the code so that I get more reward. And I don't want to change the structure of the program a ton. So we're going to assume that the person has a general knowledge of how to solve this problem, and we're going to just make it better and still understandable. So here's an example. We had someone write a program for Lunar Lander. If you haven't played Lunar Lander, it's harder than it looks. Here's a person who their program has a score of -75. Now we use POLIS. That is actually a word, but I can't remember what it stands for. It's an acronym and a real English word. So we use POLIS, and now the average score is +190. So there's a few, you can see the structure of the program's the same, but there's a few changes. There's a few changes in what action was taken. There's also a few changes in some of the constants. So let me give you an idea how this works. So this is program synthesis in general. Program synthesis often uses search. If you try to search through the space of all programs, you're going to be there forever. So normally you need to bias your program synthesis. So what we do is we've got our initial program, and then we go through line by line and try to improve that line. After a certain amount of time, we go to the next line. Now, we can use different ways of doing this. We can use bottom-up search. So just thinking about what are all the possible ways I could change the program, and very quickly we end up with thousands of changes. There's you can also use more of a heuristic search called probe. Probe is one of the more recent methods in program synthesis. It's a heuristic way of limiting the number of programs you need to search. But here's where, nope, not yet. So here's the overall structure. The program goes in, I go through each line by line. And now I'm going to say, is this program good? Well, I'm generating thousands of programs. How am I going to say whether this program is good? This is where the first time we did this, I thought it was cheating. So this is not cheating. It might sound like cheating. What we did is first we train a DQN agent. Like, Matt, why? If you can train a DQN agent, what the heck are you doing this for? Remember, the point of this was not to come up with a deep neural network that could play Lunar Lander. The goal of this was to come up with a program that a person could understand that could achieve high performance. So we've got a DQN agent that could perform pretty well, and we save a bunch of state action pairs. And then when we generate all of these programs, we run those programs against these few state action pairs to get a sense of, is this program any good or not? So this is a heuristic to help us limit the number of programs we're actually going to run through the simulator. So we use this as a funnel, get 20, 100 programs that we synthesized, run it through the simulator, and choose the best one and start over. So what does this look like in practice? Here's an example from Highway. Hopefully some of you have played this before. It's not too hard, but it's not trivial either, especially if you have to write the program. So figuring out not joysticking it around, but actually writing the if-then clauses. So here's an example. On the left, person's program has a score of -6.8. And on the right, we improved it and got a score of about 39. And what was kind of interesting is the Polis significantly simplified this first condition. That made a significant improvement. And here they looked at a slightly different variable. And then finally, Polis made this one change to which action was selected. So it turns out with relatively small changes, you can make improvements. I didn't have a slide for this, but we also ran Polis over some programs in GitHub and were able to also improve. So this was a way, I'm going to skip that. This was a way of, I've got an agent, I've got a DQN agent that's learned to play a game, and now I want to get a human understandable program for that game. So we're able to show with human subject experiments that we're able to get good code, to improve the code of people. Okay, so wrapping up. Yes, question.
Could you just tell a bit about how Polis is actually trained? How Polis is trained? Does it also use reinforcement learning?
So the Polis is not trained. It's actually more of a search method.
I see.
So
Okay.
it's going through and looking at each line and figuring out, can I change this line in terms of its structure and in terms of constants?
So the place where reinforcement learning is used is in the funneling process to reduce the.
Exactly.
Okay.
Yeah, it's just used for this funneling process to figure out which of these thousands of programs I actually want to run in the domain.
Okay. Thank you.
Yeah, you're welcome. Okay, so wrap it up. One of the reasons I really wanted to come here is tell you about, we've still got tons of questions. So first of all, we've been doing a little bit of work is trying to teach people to be better teachers. So if I've got a particular agent that's learning in a certain way, expecting a kind of human help? Can I do a 5-minute tutorial with a layperson and have that person give more useful help to the agent? Probably. I'm sure we can do it better. We could also think about, can we get our algorithm to adapt to the person? So I had the Tomas in Brazil, I had Tamer, Sable, Coach. Well, wouldn't it be better if our algorithm could learn, how is this person giving me feedback? How does this person want to give me feedback? Made a little bit of progress there, but it's pretty heuristic. Explainability. Not everyone believes in explainability. I believe explainability will be useful if we're trying to get a human and agent to work together. If we're trying to have a person give help to an agent, seems like it would be nice if the person was able to understand what the agent was thinking. And the last thing, this is an ongoing effort, is trying to figure out when is one type of help better than another. So think about Matt sits down to play Lunar Lander. I'm gonna help out an agent. Well, if I give demonstrations on Lunar Lander, I'm not very good. Those are not going to be very useful. But if I can give a shaping reward, if I can give a little bit of action advice, that's probably better. Whereas in Highway, I can actually play Highway okay. So maybe I should give a demonstration there. So this is trying to understand when a different teacher is more appropriate, a different type of teacher is better. So now I will just say, if you found this interesting, hopefully you can understand why I think it's interesting anyway, why learning from others, learning from other agents, learning from other humans, interacting with humans is useful. If this is something you might be interested in, AI Redefined has a Cogment platform. It's open source. They've signed some kind of MOU with Mila. So they're your friends. If you're interested in this kind of thing, the Cogment platform is pretty awesome. It lets you have many agents, multiple humans working together in the same simulation where you can do this kind of research. And I'd be happy to talk more about that offline. So where does this bring us? Hopefully you can see my motivation for why I think we should cheat. Why, if we want to get reinforcement learning today, working in real world tasks, we don't want to learn from scratch. I tried to give you a bunch of references, but also some ideas of where you might get this information, but also really emphasize that a lot of this stuff is very empirical, very few theoretical guarantees. We also, it's mostly, look, I got this thing working, not why or when will it be better than this other speed up method. So where I'd really like to go with this is more concrete guidelines of saying, if this is the MDP you care about, here is the type of knowledge you could use. This is the right way to leverage that. We're a long way from that. So I would love any help, collaboration, or advice you all have. And with that, I will end, and I believe we have a bit of time for questions.
Hey, Matt, thanks for the great talk. So recently I got a dog, a puppy, and it's been an interesting adventure trying to train my puppy, but this kind of leads me back to section 2 of your talk, kind of humans teaching agents. One of the things that I realized is my dog, credit assignment's quite hard. You need to shape the reward quite a bit with like lure training or something like this. But, one thing that I realized is that I'm giving it a lot of different reward functions, kind of, maybe in some type of curriculum or something, but typically with the agents that we have, the guarantees that we have is for a single reward function that's prescribed. So I guess my question is, how much do you think like continual learning plays a role in this human to agent part? Because you're going to be drastically changing the reward function, kind of like you said, the human doesn't really know what it wants. So the reward function is going to be changing quite a bit. How is this going to impact the current methods we have?
Cool. Okay, so I think I'm going to separate that into 2 questions. The first one is, let's suppose I have one task and I've got a person who's trying to give rewards or feedback or something, and the person doesn't really know what they're doing, and they're probably not the optimal trainer anyway. So one way you could think of this is thinking, well, I want to give shaping rewards. The right way to give shaping rewards is potential-based. If we do that, we're guaranteed to not change the optimal policy. But in practice, people aren't going to give perfect potential rewards. Well, you can actually prove that as long as you're giving fewer and fewer rewards over time, you can still converge to the optimal policy. So I wouldn't worry too much about those intermediate changes to the system, shocks to the system. As long as you're pushing your puppy gently without hitting it with a paper towel, with a newspaper, as long as you're gently pushing in the right direction, it should get there and still get the optimal policy, assuming that is well defined. Now, the second question, continual learning, that's a whole nother bag of worms. So if you are trying to teach, if there are different reward functions and the agent can't tell which reward function it's trying to do, then you're going to be in trouble. If it's just, I've got a reward function, but it's changing over time, then if it's changing slow enough, you might be able to track it. But at this point, I've been purposefully staying away from continual learning because I feel like I don't understand the relatively easy stuff first. But you're right, if when we're getting, when I give my dad a robot that he can train, that's absolutely going to have to be a concern. I think there's a question. Yeah.
Yeah. So you are talking about using demonstrations from humans to bootstrap the learning. So for example, for the aircraft simulation, how much demonstrations did you need in terms of time or in terms of like data set size? Anything?
Yeah. So if we're thinking, so I've got a reward function and I want to use my demonstration to bootstrap learning, then there's at least a couple of questions. One is how much data, and the other one is how good is that data? Because I might be, if I've got 50 optimal demonstrations versus 200 garbage demonstrations. And the quick answer is we don't know. But more and better, more demonstrations and better demonstrations help more. But if you, and in general, we would say, if you've got demonstrations, you should probably use them. But the idea of saying, well, do I have enough demonstrations to do something? That we don't really know how to answer yet. One last thing I'll mention though on this also is there are algorithms like Dagger, thinking about learning for demonstration, which tell you, given my demonstration set, what's the best way to get more demonstrations? Where should I get more demonstrations? So if you have a small data set and data is expensive, you can be selective about how to build up that demonstration set, assuming you have a demonstrator.
Hey, Matt, Glenn Seth, nice to really appreciate the talk. I guess I want to sort of talk about, like, I don't know if I'd call some of this stuff cheating and maybe how to think about that. Because, like as a person, and maybe as like a good researcher, I do like forms of probably like poking my environment to figure out good information that helps me learn fast. And that's like part of my skill. So is there like maybe even some more implicit ways to try and train agents that might even be able to figure out some of these like cheating methods is what you call them, but cheating kind of implies that you're not really learning stuff, but I think you still want to do that. So are there some like implicit ways maybe on like collecting more data or additional to like help the agents learn some of these concepts intuitively?
Well, so I chose cheating to be provocative because I think when most people think reinforcement learning, they think single agent in the environment doing its thing. And then as soon as you think about, oh, well, where else who could I learn from? What else could I learn from existing data? Then people don't necessarily think of that. One way I could interpret your question is saying, if I had a general learning agent, couldn't the learning agent figure out that it should listen to demonstrators? If I had a general learning agent, couldn't it figure out to listen to my dad that was giving it feedback? Then it absolutely could, but I don't want it to learn that. I just want to tell it to. But I'm not sure that was your question. So I might have misunderstood what you were asking.
It's close, but yeah, I guess if you come up with a very general agent, which I'm going to suppose I'm some version of that at the moment, I do implicitly try to figure out how to understand how to cheat. No one, at least in the most cases, explicitly telling me this is what you should do and cheat, in some cases at least. But I've learned this as part of like an implicit, like unsupervised skill that is very advantageous for learning in general.
Okay. Yeah. So one framework, ad hoc teamwork. So think about I'm running onto a soccer pitch and there's a bunch of players and I want to work together with them. And one of the things I should do is figure out how they're working. What is their policy? What are they doing? And that's something the agent should learn. It should learn that it needs to figure out to look at them. So in the case of learning from a person, if a person's saying good agent, bad agent, as long as that's part of the agent's state space, then it should be able to learn, oh, I want to pay attention to these signals and use them in this way. But if I want to if my goal is to speed up learning and not have a super general learner, I'm just going to tell it, assume that these signals are useful and assume that they're that you should pay attention to them. But in the limit, I think you're right. I think an agent should be able to learn what to cheat. It should be able to learn that I need to query ChatGPT to figure out how to solve this, write this essay.
Thank you.
Actually, Glenn asked my question, but I'm going to follow up. It was a great question. Yeah, so the word cheating also triggered me. And I wonder if there's a way to like maybe change the perspective that would make what you've been talking about today and what Rich Sutton advises us to do, kind of actually the same. And I think that's very much aligned with what Glenn was asking. So in other words, if we see the information that the agent is getting from some other agent or from a human or from a student, is just data, like just experience. And I think that your ideas about learning whether to trust an advisor or not are exactly along that line.
Mhm.
And then it's just learning. I mean, it's just inference or learning, depending on how you want to think about it. And you would be kind of a bad learner if you didn't take advantage of that information that is there. And because it's agents, then they can actively seek knowledge as well from an advisor or from some other agent and so on. So what do you think about that perspective?
Yeah, so if your MDP encompasses all of this and you can generate as many GVFs as you want over all of this, then I absolutely believe that. I think in practice, when we formulate an MDP, it typically doesn't have access to previous data. It doesn't have access to Joe, who may or may not be paying attention to right now. But if
So you just need a rich enough state space, essentially.
yes, because I'm used to formulating the state space small enough that you can actually learn something. And I'm worried. So because in the limit, you've got the entire world, and thinking about the temperature in Edmonton for how to control the chemical plant in Montreal just isn't useful. So we're going to cut that out.
But learning could figure that out too.
I could eventually possibly figure that out. If I want to get my agent making a profit trading stocks today, I probably don't want to let it spend time figuring that out. So I think it's because I'm more focused on getting an RL agent doing something in the real world now, rather than maybe the right way to really have the agent learn exactly what's useful. I think that's part of why I have this different perspective, which again is.
Okay, so the difference between what you're saying and what I'm saying is you're saying, I don't know how to do that stuff that you're proposing, and so I'm just going to use my heuristics to use the current algorithms. But I think we could design algorithms that do that are good and don't need huge amounts of data, if you're willing to like step out of the things we're used to.
It's certainly possible, but I think, and whether you or I do it, I bet somebody's going to, because it sounds like it will be cool once it works.
Yeah, last question.
Just a follow up with the same question that Professor Joshua is having. So I think it's still kind of cheating, and I like it because it's not like the data is available and you want to learn, you want your algorithm to learn how to use it. It's more like you are thinking of what data to provide to your algorithm so it can learn faster and cheat. So if it was the data that is available, the demonstrations are already there, then maybe we can try to let the model learn it and learn what is good and what is not, and when to listen and what is not. But we want to cheat. We want to know what data to give and how to give it so that it can learn faster. And this way, it may speed up when we can deploy it.
Yeah, especially if I'm thinking about learning offline, learning batch. If I've got a data set one of the first things you do is spend hours or days cleaning that data set and choosing exactly which data you want to feed to the agent. The agent could absolutely learn how to clean its own data set, but that's going to take a long time. So if we can do that for it, then hopefully we can learn a lot faster. But maybe eventually we'll come up with algorithms that are good enough to select and clean their own data and then use it so that they can learn faster on their own. So, thank you.
All right, so I'll officially end the talk. Thanks again, Matt, for this amazing talk, and thanks again for joining us. There won't be any talks next week because it's CIFAR, so we'll be back in 2 weeks. Thank you.